finished Monday, a day when homework's not due. We finished with now we have our first look at the material response to these loads, which for us means, I guess, two possibilities, and we haven't yet distinguished how we have some suspicion that one of these possibilities may happen and the other might not. The first thing we're worried about is the material undergoing some kind of deformation. It bends permanently or not, it stretches, it compresses permanently or not, but there's some deformation that the material itself might undergo that could be, in its own right, catastrophic. In other words, the machine that this is a part of might not work as it's supposed to. It might not work at all, even though it's not a complete failure of the part in terms of actual breakage, which is the other material response that we're worried about. This deformation may or may not be elastic. In other words, once the load is removed, does the piece undeform back to its original shape? It could be that the deformation is no problem, can be easily designed into the piece, can be handled. That's certainly the case with bridges. They're designed to undergo thermal expansion as the temperatures change, and once the temperature change is removed, in other words, it returns to its the installation temperature, if you will, it just returns back to the original shape, and the bridge worked at all times in between. Sometimes deformation, though, just simple deformation, even if it's elastic, could lead to failure not of the part, but of the machine of which the part is a part. We then added to this this deal that we were looking at our new measure of those material responses, and we looked at the strain, and we had two parts to that. One being the normal strain, and I defined that in what way? Remember the letter used? That was an axial, generally an axial response of the piece. Some tensile or compressive load would actually change the shape. And defined as
del over L.
And del being what? The actual change in length from the original length, and it's the original length by which we divide. So even though the length is changing as it goes through this deformation, you don't use the new length to divide by. You use just the original length, and we're going to see how that adds kind of an odd effect to some of the test data we have coming up. We'll probably get to today. How about the shear strain? Remember what Greek letter symbol we use for that? So you got to get used to these things. These are pretty standard. For all the books I've looked through and any other thing I've seen, these are common among them all, so it's an industry standard. And that's defined as not quite. Remember, it's the geometric departure of a 90-degree angle to some strain angle. And we'll look at another example of that, but it could be as simple as actually inscribing a 90-degree angle on a piece. Often it's done as either a rectangle or a square, and then actually measuring how that angle changes. So we'll do a couple sample problems to get used to those. They're very geometric problems, so be careful when you draw them. There's sometimes answers that look like they're possible in a drawing that are not really the case. Sometimes you'll see 45-degree angles where there aren't really any. Partly depending upon your skill, and partly depending upon the fact that some of these strains are very, very small. We're not talking about great large changes as we undergo this material response. So I believe we had a problem on the board for that we just finished with Friday, but we hadn't actually gotten to. All I've done is gotten down to dimensions. So let me redo those. We have some thin member under some kind of load, 12 kilonewtons. And original dimensions, original length of 500 millimeters. And original diameter, 16 millimeters. And under this load, the piece deforms, gets quite a bit longer, and since the density is the same, it also gets quite a bit narrower. So as you've seen rubber do that. As you pull a rubber band, not only does it get longer, but it tends to get a bit thinner as well. So greatly exaggerated, of course. Let's say it elongates by about 300 micrometers. And we haven't talked about what this material is yet. We haven't talked about how different materials respond to those things. We'll start touching on that, I believe, in the last little bit today. And let's say there's a diameter decrease of 2.4 micrometers. So the question is, what are the strains that this material is experiencing? Which kind of strains am I talking about? Normal strains or shear strains or both? For what's given here, we have two normal strains it's undergoing. It's undergoing a length increase and a diameter decrease. So we'd have two strains in those directions. Maybe we'll call that epsilon in the x direction, if x is the axial direction, which will commonly be the case for us in these classes. As often as not, we'll take those coordinate directions, x, y, and z. But there's also a normal strain going on in the radial direction. There are shear strains, certainly. However, we don't have any original geometry to compare this to. All we're talking about is changes in linear dimensions here. So we just have these two shear strains to compute.
Normal.
Sorry, yeah, normal strains. Good catch. Now, I believe I left you with that Monday. Anybody have a chance to do it? No, you're doing homework for me. It's not due till Monday anyway. Now it's due Friday. So you bought yourself days. So we need to look at the deformation in the x direction divided by the original length in that direction. and the deformation in the radial or diametral dimension divided by that original diameter. So do that real quick. I want to make sure, if nothing else, that you can work with the appropriate units. So let's have that answer in micros or microrads, if you wish. Microradians. So it's mostly a matter, certainly I trust you can do simple division, but sometimes the units themselves. We've got lots of very, very big numbers, and we've got a lot of very, very small numbers, and they're actually going to come into a bit of a conflict for us by the end of the day today. Just to make things even harder for us. So do the simple division, make sure the units come out right. And let's see what you get. Good warm up. You have to work your powers of 10.
That's micrometer.
Yeah. So this one of the days that you weren't here, I'm pretty sure we caught it on tape. There's about 8 different ways to show the units on these numbers, because they are, in a pure sense, unitless. But we tend to have a very small number over a very large number, or a much larger number. And so there's lots of different ways to look at these units. And you're going to have to be careful with them. So who's got what we need? Joey, there yet? Almost? The actual division of the numbers themselves is pretty easy. We've got 300 divided by 500, which is integers of 6. Is it 600 micros, though, or some other? 6,000? We got 600 here. Split the difference. Unfortunately, physics is neither a democracy nor a
It's not opinion-based.
yeah. This isn't economics, where you can do anything you want with the numbers, just to make your point.
Based on facts.
I hope they edit that out for the economics department. Oh well. I haven't been kind to the math department in all these years, have I?
No.
Is this right? 600 micros? Travis,
Yes.
you think so? Joe? Bill?
Microrad.
600 micros, microrads if you wish. Whichever. The micro just means it's 600 times 10 to the minus 6 meters per meter, or millimeters per millimeter, or whatever the units are. What about this one then?
-150.
What'd you say?
-150.
Did you squeeze the negative in there at the last minute? Negative because we have a decrease in the size, and that's reflected in the strain as well. So, fairly simple calculations when you have fairly simple geometries. Some of the problems are just a little bit more complex, but they're mostly more complex in the geometry than in the physics itself. So you just have to be careful, take your time, make a simple drawing. It helps you think through it before you actually start doing the work. Generally tend to make a few fewer mistakes. All right, that's all I had for that one. Simple as that for a start. but we're not happy. We want harder problems. All right, so let's look at another one. All right. In some way, we start with a square, whether that's an actual inscription on a piece, just a simple etching on the side of a piece, or whether it's actually a piece itself and we're looking at it as removed from the rest of the gizmo in which it works. But it undergoes some kind of loading such that it strains in something like this. So the originally is 10 by 10 inches, strains to something like this. Of course, not to scale. So due to whatever loading, it looks like quite possibly either an axial loading in the Y direction, a tensile loading, or a compressive loading in the X direction. We're not talking about just what the load is, it's just the response of the material to it. We'll look at what loads do and then figure out what this is going on as we go through this, through the rest of this term. So I have a change in dimension there. It's symmetric on the bottom as well. And a change in dimension here. Again, obviously not to scale, subject to my ability to sketch 0.3 inches in there. That's pretty rude when we're taping, isn't it? Mm-hmm. Let me make sure it's not my car. Yours is the red one out in front, Linda?
Yeah.
No, not yours either. And it couldn't be any of yours because I'm only looking at the faculty parking lot.
Well, it's a faculty parking.
All right. By my count, there's at least 5 different strains that we could calculate on this piece. I think we can find a normal strain in the X direction, in the Y direction, and a strain along one edge of that original square, because that length changes as well. I also see that there's no reason we couldn't come up with a shear strain at this corner, I'll call it Q, and that corner, I'll call it P. So, let's find those 5 strains.
Why do you have the edge? You do the X and the Y, then you're going to take that into account anyway.
It depends. It depends on what's this a part of, what your directional concerns are with either the greater piece as a whole. Steel is an isotropic material for the most part. It acts the same in any direction, whereas something like carbon fiber or wood is an anisotropic solid in that its material properties are very, very different depending on which direction we're talking about. So you might need these numbers and the diagonal numbers as well. David, what'd you say?
Because of the grain or the...
With the wood, certainly the grain. With carbon fiber, obviously fibers,
Fiber,
which way the mats are laid down.
Yeah,
And you can either decrease strains in certain directions or allow them to increase more depending on what your need with the part is. Joe?
Is that 10 times 10 inches, like any extra or something like
That's the original square, it's 10 by 10. Original square is 10 by 10. So again, mostly just a geometry problem. What I'd like is let's look at these numbers this time in percentages. I'll let you choose, it doesn't matter, we're going to have the same digits for the most part. As much as anything, you need to see how those dimensions change. Or you can do all the way across the piece and have the two changes on either side added. Ken, at the end of class, oh, I have, while you guys are working, and take time, I'll go get homework. That can pass back. If you're getting numbers, check with each other. Doing the same problem, no reason we shouldn't agree. Since I got you busy, I might as well give you back your dynamics homework as well. But then, gives you time to check your numbers. I think there's a note in the back, we'll see. That just means there's a note back in there, I want you to look at it. Okay. All right, teammates, what do we have? Got some agreement back there? Phil, who'd you talk to?
Yeah. I conferred with Chris.
Did you get all five?
I got the first two.
First, a new way to take notes, is that working for you?
Yeah.
Getting used to it?
I don't know.
You gotta give it a try.
You went straight edge.
No, but I tried. Okay.
Does it make your drawings, well, your drawings are pretty good anyway, but if you draw a straight line, does it then replace it with a real straight line?
No.
Oh, there's some drawing programs, sketching programs, they're working on a lot of them in engineering classes that will do that for you, for tablet-based classes, which would be nice. I'm just doing my best to get you guys work on paper, the old-fashioned way. All right, most of these, certainly these first three over here, the normal strains are pretty straightforward. What's the length of one edge? sorry, not one edge, but one part in the X direction, whether you do it this original length and that change, or all the way across original length and both changes, you're still gonna get the same proportion. Travis, which way did you do it?
Did the whole thing,
So the distance all the way across is,
10
no, you don't say things that way in engineering. Give me a number that I can register in my brain.
14.14.
So if you go all the way across in the X direction, then the change in the X direction is both of those on either side, so it'd be 0.6. If you only did halfway and used one of the changes, you're gonna get the same proportion. And that came out to be,
2 minus 0.6, right?
yeah, because it's decrease. Minus 0.6. And so you got, in whatever form you wish to present it,
Minus 0.042 inches.
minus 0.04, or 042 or 24? 424? And you said what for the dimensions?
Inches per inches.
Inches, yep, inch per inch, or nothing. Or you can also, of course, multiply by 100. And make it a percentage, whichever one works. In the Y direction, you get the same thing, only it's an increase in length, slightly different length, so it's going to be a slightly different strain. Phil, what'd you do with this one?
Just use 0.2 inches,
So you went just 1/2 the way
Yeah.
across.
and that would make the bottom half.
707 inches. And the strain came out to be, what way did you finally leave it?
I did 0.028.
0.028. And left it as is. Either inches per inches, meter per meter, radians if you wish, I guess, or a percentage, 2.8%. And how about the edge? The strain along one edge in that direction. Bless you. The original length in one edge, of course, is given as the original length of the square that we started with. Since this is rather big, 10 inches by 10 inches, is the kind of thing maybe that might be done on the side of a pressure vessel or something. Then what was the change? Change in the edge direction, you'd have to find that length there. And then subtract 10 from it. What'd you get, Phil? You got it?
0.071 inches.
Okay, something like that. I have a slightly different, maybe some round off. Is that an increase?
Yeah.
Okay. That's about what I got to, ballpark, somewhere in there. A much, much smaller strain. No. Oh, 7-1. Any question on those normal strains? Anybody get something radically different? Could be a little bit of round off, because
What did you have?
we don't want
What
this
did you
very-
have for that?
The original edge was this,
Yeah.
10-inch, and then now it's that.
I thought it decreased.
Yeah.
A decrease?
Yeah, the new edge was 9.93.
Well, all I can go by is what I wrote down there, but that was probably 4 years ago. It's easy to figure out. We've got a triangle now that's, this was 707, it's now 0.3, which is 677. And this side was 707, it's now 0.2 longer, so that edge is 7.27. So what's that give for the hypotenuse? I just don't happen to have it written down.
Yeah, that's a decrease.
Was a decrease, so we do need a minus in here. And in there, my notes. What's this hypotenuse come out to be?
9.93.
9.93. Yeah, clearly a decrease. Okay.
Why is that?
Thanks. So when you take it again next year, I won't make that mistake. What about the shear strains?
We got Q is plus 4.08.
Remember, the shear strain is the departure of a 90-degree angle, which we have at both places P and Q. So all we need after that is the angle they make now at those corners. That's the theta prime, and then the difference in those two is the then the shear strain. Purely a geometric strain. David?
I'm thinking gamma Q might be theta P and gamma P might be theta Q due to the properties of a rhombus angles. I'm not sure.
Gamma Q might be theta P.
Yeah. So weird idea I had.
I don't think so.
Okay.
I mean, it
No,
could be.
I don't think so either.
There is a relation between these two, but that's not the one I saw.
Okay.
I don't think it's true.
Okay. I didn't give it much thought, so.
So we can even use this drawing. Then these angles here are half of the theta angles that we need. This one being Q, and this one being P. That's a very exaggerated triangle. Yeah, 86. Yeah. This one's I think twice 47.
Yeah.
This one's twice 43. So the strain at Q, how'd you put it then?
Negative 4.1 degrees.
Negative because it's decreased, or, well, the angle itself increased, but the strain is a decrease. Sorry, it's, oh, what? 698, something in that ballpark? That's what I have. I happen to have ratings, because that's what I have down. Travis, what'd you get?
I got negative 4.8 degrees.
Degrees?
Yeah,
Oh, okay.
4.1.
Not typically left as degrees, but 4.18?
4.8.
4.8.
Should we be in ratings for this?
Yeah, it's more common in radians. Is that the .069 something in there?
0.013 radians.
Does sound like that's something in there.
No, 0.007.
Wow, the calculator is just nice, thing.
Who's gonna break the three-way tie we have?
I think, I got 4.1, huh? 4.8.
Okay, I'm taking that 4.8 from Travis. You had 4.1?
Yeah.
4.0, thank you, Travis. You guys don't need to plant mistakes. I'll make plenty on my own, thank you. So that becomes in radians. Yeah, .07,
1, 2.
something like that. I had .0698, and it's negative. Something like that. What about the other one? The other side? D.
That'd be positive.
Be positive.
4 degrees. So
Even though the angle is decreasing, we're looking at the change from those angles rather than the angle itself.
That would be positive, the same, 4 degrees.
This is going to be positive.
It would be the same number.
Wouldn't it be the same number?
Yeah.
Why is that?
Symmetry.
360 degrees and stuff.
The sum of the angles in a polygon is 360. So whatever decrease you get there, you get the same increase here. So the net change is 0. All right, any questions on that before we clean up? Let's see, let's take a quick break if you want while I reset my taper. Should actually do this twice a class, not once, since it's garbage, but it's better. No?
Okay, but
Should go back and put subtitles in.
there's some point that you can't see and can't hear
Oh.
before.
Other than that, it's great.
Yeah.
Can't see and can't hear. So it's kind of like class in real. See, I'm training you for going to RPI, where all the professors have very thick foreign accents. You can't understand them anyway. And you're going to
Same.
sit way at the back of a 400-seat auditorium,
It's
so
the
you
same
can't see
way on
anything.
RIT.
Yeah.
I had my first calculus teacher at RIT was from Chile. It was pretty easy to understand.
You can get used to it, and the third and fourth year classes are rarely in real large settings. The first year calculus and physics classes usually are very large classes.
How do they do that? Class that size.
And would you like me to stop?
What?
Would you like me to stop?
Break down.
Yeah, you might as well. The shear strain. Imagine a triangular bracket of some kind such that it looks something like this, where it's 900 millimeters on that side, 300 on that side. These two angles, 30 and 60. I'll leave it as an exercise for the reader then to figure out what the other angle is. And there's a load of some kind or other, it doesn't matter. Remember, in these strain calculations, it's merely the geometric response of the material to a load. The load itself does not come into these yet. We will be attaching those things all together in a little bit here. And it undergoes a strain such that let me just draw it this way. Of course, exaggerated. Such that point at the bottom there, point P, if you wish, drops a millimeter. So find the strain at P. Find the shear strain at P, or this bottom corner. And again, quite a bit of an exaggeration in the scale, and a purely geometric problem. It's not necessarily true that these sides come in. If it's bonded to that upper support, see that? So that the deformation, I'll draw it pink, would look something like that. That's the 1 millimeter. So I need some teaching aid. Well, this is why professors go to PowerPoint, so that they never have to suffer these imperfections in the drawings at the board. Everything's already prepared. But it's rather difficult for you to take notes when they're flying up on PowerPoints. All right, so figure out the strain. Again, what you need to do, find out what the current angle is and subtract that from 90. Might be a little bit easier if you figure out these two angles and then just add them together. And don't forget to get the signs correct. Just a good old trigonometry problem. Yep. Yeah, it's permanently bonded to the top to a rigid support, meaning there's no change in dimension of this upper piece. It's still 300, which may be used to be prettier though. use, I forget what the screen there is, I could do the same kind of thing on the board. I find it's pretty difficult to use it, sometimes you just use chalk.
When I think paper notes, I never look at it. I said paper before.
Again, probably it's easy to figure out these two final angles, add them together, that's the final angle. Got something? What's that, oh, microradians. Like that. Don't forget the micro is 10 to the minus 6. So that should be 6 moves of your decimal place.
It's
Oh. Joe? Okay, getting it? Yeah, I think that notes from there. In a second, we'll put the stress, the strain, the load, and the material properties all together. It'll actually be the start of chapter 3. Anybody else getting there? Samantha, do you have something on it? Okay, yeah, that looks about right. A little bit different than Travis's, but maybe it's round off. Don't round off too much as you're going along, otherwise the whole thing disappears. Kind of carry some numbers forward for a ways and then round off a little bit at the end. Sig figs, generally 3 or 4 on homework problems. The final angle, theta prime, should get something a little less than 90. Got something, Phil?
I got 89.904.
Yeah, exactly what I got. 89.904 degrees. Of course, in radians, you can't subtract that from pi over 2. I hope you realize. And something then like 0.001796. That about right, Phil? That's in radians or radians over 6 places. And we get something like 1796 microradians. Phil, about like that? Okay, Joey?
Not yet.
All right. But it's a geometry problem, so maybe a little more time, maybe a little bit bigger drawing. What you can do is find the now the length of this, I guess it'd be the height of the triangle, and then you can use that height with the other 2 sides to figure out what the angles are, and then add them together. That's one way. I don't really know another way to do it. Phil, you did that?
Yep.
Okay. Questions before we move on? This is actually what we need for chapter 2, so we're going to start nicking into chapter 3 a little bit as we start actually bringing the material properties into account here, because you can imagine different materials strain, stress, and deform very, very differently than other materials. So now we can finally bring all this in together. So any questions about that before we go off? Okay. The most common way all this is put together is with what's simply called a tensile test. And of course its reverse partner, the compression test. Usually what's done, though there are variations of course, a test piece of the material supplied usually by the manufacturer is made such that there's two big fat ends where it's threaded and then fastened into the machine, the tensile test machine, and they just simply thread it right into the I believe they're called the mandibles at either end. This test length here generally is about 2 inches. So they might actually put little marks on the piece itself and then use those as an indicator of how much the piece is deforming in that axial direction. So this is typically about 2 inches, with a round cross-section on the piece. And then the mandibles move apart, putting the piece under load, and the deformation is monitored sometimes with the machine itself. They can just tell how much farther apart the jaws are getting. However, that's not very useful because that's over this original length, not over that original length. So they they usually will put on an extensiometer of some kind that will actually record the elongation of the test section there in the middle. Most of these test pieces being of very standard sizes, then the machine knows L0, which is usually the 2 inches there. Can then compare it now to the deformed length, and from the difference between those two get del, and then you have the normal strain. Of course, the machine can record what is being needed actually this piece. The test piece if it's easily a part of the calculation. So then the output from this test will look something like this. On the y-axis is the load, either in terms of P itself, but more likely in terms of P divided by the original area, which we know as load is typically normalized over the original area. We know that as, well, yeah, this is the cross-sectional area, this area of the piece there. But the ratio of the load to that normal area is the normal stress. So on the y-axis we have the normal stress, and then on the x-axis we have the elongation, the difference between the the extensiometer measurement of length divided by the original length, which we know as, of course, then the normal strain. And then as the piece undergoes this test, those two are plotted against each other for a particular material. And it's reasonably characteristic of the material itself. The only variation from one test to another of the same pieces is just minor differences in the manufacturing of the material itself. All right, all set? All set to turn the machine on? And if you go to Angel, I've got some videos of these very tests going on. They're not the most spectacular tests to watch, other than occasionally the compression tests are pretty exciting, because when the piece finally comes apart in compression, it sometimes does it in a Hollywood manner. Explodes all over the place, pieces flying, and then you can hear all the test guys in the background whooping and hollering like it was a Mythbusters episode. So, the test goes then something like this. Starts at very low load, just start turning on the machine, let it start pulling apart the pieces. So P is very small, A0 is very small, and the piece is not deforming very much. These are at the early loads. What's interesting to us is the fact that this early part is very linear. Most like this aluminum, most type of structural solids we have a very put down the have for low carbon steel. Just so you get an idea of what some of these numbers are. Very common structural steel. So the test goes very linearly. The load increases, and the response of the material, the deformation, is proportional to that load for a good section. If for some reason in here, for a coffee break, or the union says they must take a break, they turn off the machine, let the load go back to zero, the material will go right back down that line to its original length. No deformation when there's no load. It retraces this part of the curve almost perfectly. A lot of trust in that happening is a big part of structural design. That as the loads change, it's very, very predictable what the response of the material is to those loads. So it's very important. This region is a very, very important region because it is so predictable. So operators get back from their coffee break, turn the machine back on, go right back up this very same curve, and let it keep going a little bit farther this time. Until some point when the linearity of it starts to, it departs from a linear response. It starts to turn over a little bit. In this case, as the load increases only a little bit more, we're starting to get more of an elongation of the solid itself. So we're starting to increase our distance down the y-axis or x-axis. Put a couple numbers on these for the material solid. This strain down here is sunk 2. The load there, give or take a little, about 40. The extreme difference in the scales of these is a small number. This is a very large number in comparison. Here, in the linear one, we can make the scales anything we want, but it starts to get in trouble as we go through this. There's 2 points of interest that happen very quickly in here. The first is this last little bit of linearity is called the proportional limit. Soon after that, though, the material starts to get longer, starts to deform much more than it had been before, even with no increase in load. The load can be left the same, let them starting with itself. In fact, this region then, and it may actually dip down a little bit as the material really starts to stretch. This piece, this point, somewhere in there, and there's different ways to pick that point, but it's a fairly standard point up there. It's called the yield stress. Because it's here that we're leaving the elastic region. Remember, this was all an elastic response in that the load was relieved, the material went right back down that line. If the load is relieved now, the material tends to go down parallel to that line, more or less, but left with a permanent strain in it, even though the load has now been relieved. So this first region here is the elastic region. The second region here is called yielding, or the yield zone. The end of that, and this is where the curve then starts to turn up again. As the load increases, now the deformation of the material isn't as increasing quite as fast. This region ends at about 0.02. And the material, as the load increases, tends to go up something like that, then starts to flatten out yet again.
For low carbon steel.
For low carbon steel, or materials like low carbon steel will have very much the same characteristic curve, just the numbers will be different. And as part of the designer, the reason different materials are chosen because we need different responses in here in this elastic region. This is where almost all of the engineering design is, because it's predictable, it's elastic, it's a long way from any kind of catastrophic failure, either by deformation or by the piece breaking. All the piece is doing so far is just getting longer and longer. This region in here is called the strain hardening region. It's not going to be of great interest to us because almost all of our concern is going to be down here in the elastic region. But to material scientists, this can be of a lot more concern. So that's the strain hardening region. Then after this, and you've seen, if you've looked at the video, you've seen this, the material has not had an appreciable change in the cross-sectional area. So all of this region is pretty much as divided by the cross-sectional area in calculating the stress. But then from here on, the material starts to go from this nice, generally cylindrical shape that it has in here. It starts to do what is called necking, where at a region somewhere in the middle, it actually starts to decrease substantially in its cross-sectional area as the load increases. And you can see that if you look at the videos carefully enough. I think one of the videos, they even stop it right there and say, you can see that the material is necking now, and they even put an exclamation mark after it because it's a very exciting time. But there's an interesting thing that happens with the graph itself. Since the area is decreasing, if that's not taken into account in the calculation, then the curve tends to go something like that. That is mostly an indicator that the area is decreasing in the real solid, but the calculation is with the original cross-sectional area. So this is still quite big. The material is it appears as if the load is actually going down. The stress is decreasing until we get to a point where the piece ruptures. There's actually material failure. The piece cracks across there, and the test is over because now the piece is completely destroyed. And this is sometimes called the breaking stress. That comes at a value of about 0.25. Oh, this was about 0.2 back here. This region is called the necking region, where that pinching of the area is occurring. If, however, if the curve had been calculated with this new cross-sectional area, the actual cross-sectional area, the curve would have gone more like this, and then ruptured at the same place. So that's using a actual. This is with a original, which is no longer the true cross-section area of the piece because of this change in cross-sectional area. This extensiometer, if they'd left that on here until it ruptured, that would have destroyed. So this is typically taken off when they notice that the linear region has stopped and they're now into the greater material responses. The piece is no longer on there measuring this difference in length. So things do get more approximate from then on. It's also, though, typical then, once this piece is broken, they're put back together on the lab bench, and the actual distance between these two original dots is measured to check this strain at rupture, the normal strain at rupture. So that's the typical curve, specifically with numbers to low carbon steel, but it's the general curve for what are called ductile materials. Ductile materials are those that have this kind of response at generally room temperatures, and that's pretty much where you want to design for things, is at room temperatures. Okay, there's an introduction to the stress strain diagram. We'll talk more about it on Monday then.